Hi, good evening, everyone. I'm Emily Morris, founder and CEO of Emrgy. Thank you so much for having me here tonight. It's a pleasure to be here with all of you to talk about a renewable topic that isn't exactly the sexiest or most popular, as we see a lot of solar and wind, as we all know, hydropower. But I'm super excited to be talking about this topic with you all and introducing you to Emrgy's concept. Without further ado, I assume everyone in here is familiar with conventional hydropower, like the image here. I know I met some folks already tonight that own and operate their own hydropower systems. Can I get a show of hands of anyone who's actually operating or dealing with, hands-on with hydropower? A couple of us? Okay, well, we all should know, or should acknowledge, hydropower being the oldest, the most oldest form of renewable energy, and many other really attractive attributes about hydropower. It's the most reliable, it's the most continuous, it's the most controllable form of renewable energy. It allows us to have a resilient power system, which is why it's the backbone of national electric grids all over the world. And hydroelectric like this is really the basis for what has spawned the industrial and other technological revolutions of our recent history. So hydropower is great. We should be building more and more of it, right? Well, unfortunately, we're not building a lot of dams like the ones you see here anymore. As we probably know in this room, they can be very environmentally destructive. In fact, there's many different campaigns for reducing the number of dams around the country. They can be very expensive to build a very large facility like this. It can take, on average, over 12 years from ideation to commissioning of a hydropower project, given the type of permitting that's required, especially around environmental sensitivities. And as more and more communities or states or even countries start making very aggressive sustainability goals, going to 100% renewable or going to a carbon-free future, the question is, where is this energy going to come from? It's unfortunately not going to come from hydropower, given that the average age of a hydropower dam in the US is now over 80 years old. Most likely, it's going to come from something that looks a little bit like this. Now, can we see a show of hands of people who have actually touch and feel things like this on a more regular basis? Yep, I see a lot more hands in the room. And there's a good reason for that. These systems are cost effective. They're rapidly manufactured. They're able to be installed very quickly. They're standardized. They're modular. They're replicable. There's many, many exciting things about solar. You have other things to add into. I think there's a lot of good attributes about this. And most importantly, the cost is being driven down, so we're actually able to acquire these types of systems more cost effectively. However, we know that these systems don't operate 24/7. We know that we can't control when the sun shines. We can predict it, but we can't turn it on at our 6 p.m. evening peaks or things like that. And so there are some inherent challenges related to the intermittency of systems like this that you see here. Despite that intermittency, it's projected that by 2022, almost 90% of all new renewable capacity that's coming online is going to be either from wind or from solar PV. So we see this growth not just on our rooftops, but also in the data, as you see here. And so when we look at how hydropower just is not able to keep up with the eclipsing amount of solar and wind that's coming online, we have to be asking really tough questions of what do we do about having a sustainable grid 24 hours a day with intermittent renewables. There's a lot of conversation about energy storage, mostly still chemical options. And we all know that the pricing of those types of systems is not where it needs to be able to have a sustainably renewable future. So we see water movement as the world's natural battery. We have water infrastructure, particularly in our case, we focus on water infrastructure as opposed to natural rivers and streams for many of the reasons I mentioned earlier about permitting timelines and environmental sensitivities and wildlife protection. We see water infrastructure as a source of natural energy storage that should be able to be tapped into for our use. These are areas that you cannot build a conventional dam. They don't have major elevation drops or even small elevation drops. These are the kinds of waterways that must continue to run in order for our crops to be irrigated, in order for people to have drinking water, and to serve many other commercial or industrial purposes around the country. And so what we're doing here at Emrgy is we're taking a product style similar to solar and wind that is repeatable, that is modular, that is standardized, that is able to be manufactured rapidly and at low cost, but applying it to a medium that is controllable, that's reliable, that's able to be harnessed and applied for our good. And so this is a photo of one of our systems that's here installing, or that is here operating, only about 20 miles from here in South Boulder. So this is an energy asset owned by Denver Water. This water here that you see going through the turbine will eventually become drinking water. So you can feel proud that perhaps some of the water that you've had to drink in Denver metro area has actually been used to generate clean energy in distributed hydropower first. And essentially what we do is we have developed a low impact way to distribute hydropower along these channels as opposed to centralizing it in one major facility, which is what hydropower has traditionally been about for hundreds of years now.
What about the fish?
So this is a municipal water supply canal, so there are no fish or wildlife in this channel. And that's another reason why we focus so closely on water infrastructure as opposed to rivers and streams. These are all brownfield developments, all retrofits. We don't put these in the stream behind your house or anything like that. That said, I will talk as we look at the technology about attributes that we've included in the system for wildlife compatibility, although we don't target those areas whatsoever. And so, when you look at the intermittent alternatives in distributed energy versus a distributed hydroelectric opportunity, what's important to note is that all types of distributed energy can essentially achieve the same amount of capacity, just depending on how many modules you install. You can have a comparable amount of solar panels, wind turbines, and distributed hydropower modules. But the interesting thing about hydropower is that it can run almost all the time. These water supply canals can often, can be running 24/7, or perhaps they come down for maintenance a couple of times a year. But if it, say, ran 80% of the time, which is what you see here, then over the course of the year, that same investment into the same amount of power for wind, solar, or hydro is going to result in far more energy over time than the other alternatives, just because the resource is there more often. And so this is just an illustration. Not all canals are the same, and obviously some areas have better solar resource or wind resource than others, but the opportunity for using distributed hydropower to be that combination of both stored energy and energy generation is an exciting opportunity for hydro in general. So let me tell you a bit about our specific project. We deliver product that is fully assembled and ready to be installed. This is, you may actually recognize this vista. If you've done any hiking or biking around Ralston Reservoir here, this is, as I mentioned before, Denver Water's property, not too far from here. But essentially, you know, one of the important parts about distributed hydro is we have to take those lessons from solar and from wind and having something that is ready to be installed when it arrives. Most conventional hydropower is constructed at the site and assembled together to become a construction project. When we look toward distributed renewables, these systems have to be brought in, installed quickly, and interconnected quickly. With the smaller power densities, there isn't enough, say, capital cost and budget in the project to be able to spend lots of time building up things on site. So at Emrgy, we've partnered with GE Hydropower. They manufacture our turbines for us. And so when we deliver product, it comes straight from their facility on a truck that can be driven up right to the side of the canal. That's another important attribute about water infrastructure, is that they have very good accessibility for heavy equipment, for electrical interconnection, and for delivery. We don't want to drive these kinds of trucks all through, you know, the hills behind our house or anything like that. Once it gets to the site, we simply lift the unit off of the truck, place it right down into the channel. It comes in a fully self-enclosed precast concrete box that is made of the same concrete that lines the canals. So we know it's going to live for a very, very long time. It's going to be robust, and it includes everything needed to be able to keep the shafts plumb, to have everything pre-tensioned and pre-tightened. And essentially we have here two twin vertical axis turbines. These are kinetic turbines rather than pressure-based turbines. So these really capitalize on simply the flow of water through the channel, not on head pressure or on an elevation drop. So essentially, these two work in tandem. They are hydrodynamically optimized to work together, and actually, you know, the efficiency of both of them next to each other is actually higher than just one or two on their own. And so we essentially dropped this full system right into the canal using a very simple crane, like you see on the right there. We actually did rent this crane, but Denver Water actually owns a crane on site that can be used to move these in and out of the channel as they please. And then we just sit them right down onto the floor of the channel. We don't modify the structure in any way. We do we don't do any anchoring. We don't do any diversions or any additional changes to the channel whatsoever. So once they're installed, they simply sit there. They're held down by their own gravity and are unable to move with worst case water flows. And then as the water gets turned on and flows through these units, we scale up the power capacity by putting arrays in series inside of canals. And so it's intended to be an extremely low impact solution where you can place them right down in the channel and connect the units together, aggregate the power, deliver that back to the grid or to a net metering or behind the meter arrangement with the water asset owner. So I'll walk you just briefly through some of the technological features that make our distributed hydro option unique. We essentially, our product consists of three major subsystems. We have our flume, the precast concrete structure I mentioned before. We have the hydrokinetic assembly, and then we have our power system. So when we look at the flume, it's intended to be very simple. This is our gravity base. Beyond that, though, we do some engineering, and a lot of engineering is embedded into these systems to keep them very simple. As I mentioned, this is a hydrokinetic system, meaning it operates based on the flow of the water. So you can imagine it much more similarly to a wind turbine than perhaps to a hydro turbine. So in wind, the faster the speed, the more power you get, which is exactly the same principle here. And so what you'll see is we've actually created and engineered a radius, a hydrodynamic radius inside the concrete wall that acts as a flow accelerator. You can see here in the top image a velocity gradient without any acceleration using the concrete. Here, what you see is once we radius in this concrete, a really high acceleration of velocity right where the turbine comes and harvests the torque that's going to be converted into electric power. Simple designs like this have allowed us to really increase the power density of these seemingly very simple units. And so this flume is actually a very important part of our product, not just from the standpoint of maintaining our customers' wishes, that they maintain the integrity of their canal in full. They still have everything ready and able to operate the water flow as needed for municipal or agricultural purposes, but yet we're also able to use it from a performance standpoint, adding to the power density of our units. When we look at the turbines, we have spent hundreds of lab tests and simulations looking at how we can utilize a vertical axis system rather than perhaps what you may have seen in other concepts of horizontal axis looking like a wind turbine, a true wind turbine, to be as high efficiency as possible. We believe that vertical axis is the most applicable type of system for distributed hydro in that it's able to maximize the water column while also take advantage of the mechanism of how the water flows through the channel. And so we have a whole team of hydrodynamicists who have assessed many different turbine types, and we spend a fair amount of time not just looking at how the turbines interact, but also how the series will interact. When you think of, when you drive by the NREL site close by or other wind farms and you see the orientation of different turbines, to be able to take advantage of the fluid as it moves through a series of different operating machinery, our system works in a very similar way. So we configure our arrays in a very specific way so that way, as water flows through, we're able to capitalize on the wake of each unit, either in front or behind, and optimize the power performance. Interestingly, we've been able to demonstrate here in Denver different operations in flow regimes where perhaps, this year actually here in Colorado, there was a series of wet months where we were getting so much water flow, water into the Ralston Reservoir that they actually didn't need to run the canal upstream, which is where our turbines are. So we fell into quite a low flow regime for a series of weeks and months. And one of the interesting optimizations that came out of this was we were able to take some of the downstream units and overspeed them, almost operating them like a motor and bringing water levels up in front of them, adding a bit of blockage there, bringing water levels up just a couple of inches to push those units upstream into their optimal operating range. And so there are array dynamics that we are on the forefront of discovering to how you can utilize these systems in connection with the clients. Because one of the unique parts of this type of industry is that it is, while there are weather impacts, just as I mentioned, having excess rain in downstream reservoirs or things like that, there is a whole aspect of operational efficiency and operational excellence that can be achieved to be able to run the canals for power generation. And to be able to coordinate the operation of these systems with the water asset owners' operations in general, so that when they fall into that low flow regime the next time around, we can already proactively anticipate that, begin to operate in that mode, and be able to maximize the amount of power that they're able to get out of that in light of the operational regime that they have. So moving on to the power system, I decided not to bore you with a long electrical diagram of how these systems actually come together and aggregate power for the grid. But what I decided to show you here is something very simple. The electrical side of the business is not an area that we innovate. We focus our innovation on how we take energy that's inherent in water flows, how we convert that into meaningful, usable energy for our customers. And everything from these very simple off-the-shelf induction motors to the grid is all commercial off-the-shelf technology. Now, of course, we embed our control systems that perform these array controls and optimizations on them. But in fact, we're using one of your ABB units in a very simple NEMA 4 enclosure to be able to perform those activities onto the units. So this is an area where we really want to focus on developing distributed hydro in the most sustainable way possible without introducing any new risk to the grid or to our customers who need a very reliable power system. Interestingly, I was having some conversations before this talk out in the atrium, and we were talking about why this technology or distributed hydro didn't have a robust industry the way that distributed solar or distributed wind does, and sort of why this is still a very new concept. And while hydro has been something that is obviously been invested into and researched for many, many years, as it is the oldest form of renewable energy, distributed power systems are a fairly new thing from a grid connection standpoint. And so really the development of the power systems, I'm sure when many of your ABB systems like the ones we use certainly weren't developed for distributed hydropower and probably were developed for other distributed systems. In fact, we began using the configuration that we have based on recommendations from some of the NREL wind professionals, and being able to take from more mature industries, take from over-invested industries to apply here is something that has really enabled distributed hydropower to be able to be a commercially viable option. Before this, and before solar and wind were able to invest and develop those types of grid-side infrastructure, it was very, very difficult to be able to successfully and sustainably deploy a system like this. So all that to say, the power system is where we try to keep it very simple and learn and take from the other industries that have done it far better than we could invent on our own. So summing that all up, what ends up happening is our units are about the size of a large SUV, say the size of a Hummer. And we deploy them in twins, as you can see here, for all the benefits that I mentioned before. They're intended to be very simple. They're intended to be able to integrate seamlessly into existing flows of water, and to be something that seems very familiar when I have many clients who will look at something like this and say, this looks like, you can fill in the blank, something that you recognize. It looks like a pinwheel that you blow, or it looks like an egg beater. It looks like something that you can imagine and that you've seen working in operation. And when you see it turning in the water, it's very familiar, as opposed to perhaps something that is a black box in a canal that you don't know exactly what's happening there. Our goal is to keep it as transparent and as simple as possible. So I'm sure you're wondering, where is all this infrastructure that we can put these? And we have the same question. Unfortunately for us, we don't get to go to the NREL website and type in latitude and longitude and have all of the distributed hydro locations spit out for our convenience. If anyone here works at NREL, please tell them that we would love to have something like that. Maybe I should go to the JCRES and tell them that this is what we need. What we've done to try to understand what this opportunity is we start with DOE estimates on where hydrokinetics could be applied, both globally in terms of both onshore and offshore opportunities. Then we said that doesn't really make sense because we're not an ocean technology. We're not trying to put this out there. We got to narrow that down. And so then we looked at rivers and streams, and we're really not looking at rivers and streams. We want to find the infrastructure of where we can install this. And so instead, what I ended up doing, I think I lost the award for Best Boss of the Year, is I had an army of interns that mapped every single mile of water infrastructure in GIS by pulling in information from the U.S. Geological Survey that's released every 5 years, and actually transcribing or translating both GIS or USGS data with Google Earth resources to map out all of the characteristics about these sites. These are, you can see California here, we have Washington, and essentially we're working our way west to east, mapping every water infrastructure location that is ripe for distributed hydropower. What we do is we take in all of the USGS data, we then filter through to only artificial streams of water, and then we run that through a 9 criteria algorithm that includes, is it concrete lined? Is it free of fish and wildlife? Is it used for navigation? Is it close to power grid interties? Is it free of debris? Is there, we also overlay a spatial analysis tool to understand what the slope of these channels are, to understand how sizable and how compact these series or arrays can be. And essentially what we've now garnered is a database of about 15,000 miles of water infrastructure here in the US that's been pre-screened for distributed hydro. This is something that we'd love to potentially eventually share with broader communities, and we hope that this is the start of the development of an industry. But so far we've had to sort of define this from the ground up in the absence of cited references. That may seem like a lot, 15,000 miles, but when you can look at other countries around us that also have significant agricultural infrastructure, there is, I was just talking with some folks from Taiwan last week where there's 68,000 kilometers of concrete-lined agricultural infrastructure there. Our neighbors to the south in Mexico, something around 40 to 50,000 kilometers of water infrastructure. And so while, maybe distributed hydro isn't necessarily these huge figures that are coming out of DOE reports for what the oceans or the tides may be able to offer us in hydrokinetics, infrastructure is a fabulous place to start building an industry, building a mass of distributed power resource that can really move the needle toward a more distributed, sustainable grid and sustainable future. And so we hope to be on the forefront of that and hope to see a lot of additional development around that here in the US and globally as well. So looking at this database, I'll tell you a little bit about how we, practically how we cite locations for distributed hydropower. The modules, as I mentioned, don't use any anchoring or other type of construction. And so fitting them into channels that are sort of box-shaped, that are almost like a chute versus your traditional sort of trapezoidal irrigation channel, or even earthen-lined channels can be applicable. We really look for sites that aren't tiny ditches though. As I mentioned, our twin system is about the size of a Hummer. So if you think when you see these types of channels, could a car or could an SUV sort of fit down in there? That's really the meaningful size that you need. You could certainly do smaller systems, and I'm sure some of you have probably seen the YouTube or viral videos about the camping style sort of floating buoys that can charge a cell phone. Of course, you don't need a large channel for that, but what we're trying to do is not necessarily assist in in off-grid living, but develop a more sizable alternative to your distributed solar and wind. So we're looking at megawatt, multi-megawatt installations. And in order to do that, you really need a sizable unit that can capture, at least 7 to 10 kilowatts per module. And then you need to multiply that by 100 units to really get to that sort of megawatt scale. And so we seek, sites that have the appropriate sort of dimension to fit a car, 3 to 9 feet of water depth, where places where you can have equipment, heavy equipment come in and actually deliver and install these systems, and the access to the power grid. Once there are sites like this, then we run a series of hydrodynamic and hydrostatic simulations to look at what is the power potential in these types of sites. And so we look at the slope of the channel, we look at the discharge, and we're able to put together a flow profile and overlay that with an energy profile that distributed hydropower could achieve. We use this as an Army Corps software called HECGRAS that some of you may be familiar with. It's used in hydrology quite often. Where's my hydrologist around here? There she is. And then we work directly with water asset owners to microsite each of these units to have an optimal array. You may be wondering, well, why are these closer together and why are these further apart? That's really where Emrgy excels in our intellectual property. So I know I've talked a lot about how this is super simple and anyone can do it, but really understanding how the slope of this channel changes over the operation of the fluid, and understanding where water accelerates, where it slows down based on geometric changes or elevation changes, to be able to optimize the power output of a system while minimizing the hydraulic impact or the impact on water levels is a very complex equation that is done through more sophisticated modeling. And so, we hope that one day we can refine this process to something that is very rinse and repeat. I was talking with someone recently who was telling me that, the first time they installed solar panels on their roof, it was, 20 years ago, and they had 4 different site measurements, 4 inspections. They had all kinds of simulations looking at the angle relative to the sun, and now they just replaced their system, and they had one intake form on a website, and it was optimized and done. And so we do hope that there is optimization in this process, that eventually, especially as a distributed hydropower industry really develops, that the ability to site in a more convenient, more straightforward, quick way will be developed. But today we do a good bit of hydrodynamic analysis on every single site. And so when we talk about job postings, we're always looking for folks who can help optimize this process as well. And so, from there, once we site out the array, then I'm sure you're wondering, how much does a system like this cost me? And what we continue to make the automotive analogy where these are about the size of a large SUV, and they cost about the same as a large SUV as well, between $40,000 and $50,000 a piece on the equipment side. Now, our new partnership with GE, we hope will reduce those costs much quicker than we could do on our own, because of course they've got a little bit more buying power than a tiny company out of Atlanta asking manufacturers to make our equipment faster and cheaper. But as we continue to drive this down, what's important to note about this slide is not the actual numbers, because the truth is that every site is different, and we do a customized proposal for every site. So it's important not to get hung up on the specific numbers. But what this slide is intended to illustrate is that even though the cost of the equipment is going to be a little bit more, a bit higher than, say, your average solar panel or solar equivalent, what you see is that we are really targeting areas where we can install these, and they're going to operate 80% of the time or more. And if that can be achieved, then the cost of energy per kilowatt hour can be really competitive for a distributed system. So I'm not talking, multi-gigawatt utility installations here. I'm talking behind the meter or net metered medium scale installations. This can be an extremely economically competitive solution in areas where water flows often near continuously or continuously. When you compare that with similarly sized medium scale alternatives, it becomes very competitive, even though it is a new and emerging industry. So we work with customers really in two ways. Water asset owners can invest in the array themselves. That way they, often these types of water flows are owned by either governments or quasi-governmental agricultural entities, and who are making money today through selling that water, either selling it to people like us for drinking water, or they're selling it to farmland. And so, remonetizing that infrastructure to be able to sell power is a new revenue stream, a new opportunity. So we offer the opportunity to invest into the system and to be able to take the profitability from that over the long term. We use the same equipment as hydropower in terms of shafts and bearings and gearboxes, and so the life cycle, while we advertise it to be 30 years, as you saw on the previous slide, should be, if properly maintained, a very long time for them to be able to realize the benefit of hydro as they run their system. Or we also offer the opportunity for them to simply host an array. So that would be similar to other types of renewable project development, where they would offer the water flow and be paid essentially for a lease payment for being able to use that water flow. We would develop the project ourselves and develop the utility relationship or the commercial or industrial relationship for entities along the canal to be able to net meter or use this behind the meter. And at the scales we're looking at today, with sort of from the 100 kilowatt to 2 megawatt range, this makes the most sense for us to be looking at net metering and behind the meter opportunities. So that's a brief overview of who we are and our view on distributed hydroelectric power as we see it today. Obviously, I'm one person in this emerging industry, so I'm sure there are many other ways to develop or invest into the development of distributed hydro, and I'm happy to open a conversation or a dialogue across the room with any questions that you might have, or any other topics that we may want to cover for distributed hydro as well, because I think we have a good bit of time to do that. Yes?
Can you tell us more about the generators themselves? Do they have the built-in inverters? Or?
Yeah, so today what we're doing, as I mentioned, we are keeping things super simple. So we use every system is a 480 volt, 3-phase AC induction motor. We use those both as generators and as motors. So motoring is actually the best way to clear debris, interesting fact. So essentially we take this wild AC that's coming from the variable frequency of operation. We use an ABB drive that acts as what we call our turbine controller. Every turbine has its own controller that is essentially an ABB drive that it does both rectification and inversion in the same box. So that conditions the power there. It also allows us to maintain the optimal rotation speed relative to water speed and control the performance. From that box, it's with some auxiliary equipment in a NEMA 4 enclosure that can sit either atop the unit in the canal or on shore. And essentially coming out of that is 480 volt, 3-phase conditioned power. that we can run either directly to a behind the meter application or aggregate along the channel to a more sort of grid side switch gear. Yes?
Can you talk more about the competitors in this space that you know of?
Yeah, so to be honest, there's two ways to define competition, right? One, I think traditionally people look at competition as what technologies look the same or who's developing similar technologies. And on that, to answer that question, most of the folks who are focused on hydrokinetics are developing it in an oceanic or international focus. And the reason for that is that the prices for power, feed-in tariffs, are much more attractive for hydrokinetic in oceanic environments in Europe and Asia. So a lot of the folks, even folks that have developed isolated pilots here in the US, for example, there is a pilot that was developed with the US Bureau of Reclamation back in 2012 in Washington State. The owner of that company, I spoke with him in the last year, and he told me that they're over in Scotland, I think it is, trying to get in on the oceanic environment. So it's really hard to compete with higher priced, product in an area where prices are going further down all the time. Now, where we see competition is not necessarily whose products look the same, but who is offering solutions to the same customers that we are. And it's very rare that I walk into a water district that says, oh, I haven't ever thought about renewable energy before. Everyone I've talked to, of course, says, well, the solar salesmen tell me I can get this, or the wind people say I can get this, or there was someone who came here and wanted to build a dam on my canal, and I couldn't do that. There are proposals to cover canals with solar panels, which is of course feasible from an engineering perspective, but these canals are actually quite interactive. They have to maintain them and have access to them, so that hasn't gained much traction yet. But it's a very real proposal and a very, solar can be very cost effective. So we would see typically customers are not choosing between our flavor of distributed hydro and XYZ distributed hydro. Typically they're choosing between a solar option and potentially something like this, or actually one of the more common things is trying to pool their resources to be able to buy into a giant utility scale, either solar or wind opportunity that is potentially quite far away from where they actually are.
So not much.
Not much, but there is advantages and disadvantages to that, right? We of course are enjoying the opportunity to have some first mover advantage and to be able to have a commercially available option for this. However, there's a reason why solar could never have gotten to the pricing that they have gotten to now if there wasn't a whole industry, a whole development of lobbying efforts and collective activities to bring that solution to where it is now. And so it's very hard to imagine distributed hydro becoming that competitive when there's one company, singing out in the distance wanting this. And so, we are really encouraging and trying to help build a community of distributed hydropower believers and encouraging of trying to get different methods in there, because while we have spent 5 years and in terms of research much longer developing what we believe to be the best technological product, there's many ways to convert energy and water into electric power, and to be able to do it in a low impact way, hopefully more people will be able to jump in on this. Yes.
What kind of computing power do you need to model that flow and how to space those?
It's a great question, and one that I wish I had one of my fluids folks here with me. We use a cloud computing service. It's a fluids program, a CFD program called SimScale, and it basically is an open foam base with a wrapper, and we do all of our computing in the cloud. And so it is a lot. We sort of burn through core hours, unfortunately, a lot faster than I would like to. But as I mentioned, we're still very intensive about performing detailed simulations of every single site that we look at, and we hope that as we develop more operational history, more field data that can be replicated and translated into new opportunities, that we won't have to be so intensive on that. But today we are. We use fluid dynamics modeling both for site development and for the sales effort, as well as obviously for product development too. So, yes.
Like you control the motor?
Yes.
You don't do that remotely?
Yes.
Each unit is connected?
Yes. Yeah, so in addition to each unit having a turbine controller, there is one at the grid connection point. We have an array controller that essentially allows for dynamic control, but as I mentioned, in those high or low flow regimes, to be able to control the different machines relative to one another. Yes.
Does water flow 100% of the time?
It depends on where you are, and it's a very interesting, macro dynamic that books are written about, and I'm sure some folks in this room have studied water development in the West and water rights, and so in our world, it's a very fascinating, selection of target clients and target markets, because we're not just looking at where does what rainfall or where are weather patterns attractive. We're looking at who has contracts to run water 24/7 and who has federal contracts, because those are going to be more sustainable long term than, say, fishery contracts or other potentially seasonal type of contracts. There are some variations regionally. If you're down, in the extreme southwest, there's several bureau and other canals that are running almost all year round. Several of our clients in Arizona, they shut out just for 2 weeks a year just to clean things out and keep running. In other areas, here in Colorado, it's much more seasonal. In Central Valley of California, you see a relatively seasonal water year between February, March to September, October. And then, there's different uses of water too. So all of those examples I just mentioned are roughly all water conveyance for the purpose of irrigation. Another great application of this that I didn't even talk about in this presentation is the integration of these systems at existing hydropower facilities in tail races or in intakes. This is a great application to add capacity to an existing dam without compromising the integrity of that dam. And that is very centrally what we're looking at, particularly internationally, because those areas are so well developed already. And in those cases, those systems are already operated for the purpose of generating power. So they may not be continuous, but they're operated based on power markets and when pricing is most attractive for generating power. And so we hope that over time, through the introduction of these systems, we can show water owners and water companies that are moving water that there are advantages to selecting when and how much water to run within, of course, the confines of being able to complete the water deliveries that they need to. But yes, it's a spectrum. There are many continuous flows, but there are many seasonal or non-continuous flows too. Yes.
So do you look for pump stations to power with your
distributed, I mean,
Yep.
use it locally rather than trans.
Yeah, absolutely. Those are excellent opportunities for this, and that's really where you'll find farmers who are using diesel for that, or we see a lot of diesel usage rurally, and to be able to replace that diesel with even just one of these is an excellent statement of sustainability. And what's challenging for us is that the sales process for that is very different, going and finding individual farmers who not only have the ability to make those purchasing decisions, but have the permissions to do that too. And so I would say we as a company are a bit less focused on that, but partnering with dealers or partnering with folks that supply those types of generation systems is absolutely a great opportunity. And even some of our irrigation districts use it to power their pumps or their wells, as opposed to conventional means.
How long have you been doing this, and how did you settle on a vertical axis rotor?
So I came into this business really from defense contracting, and in fact, Emrgy's product started there. So I was building with a team of engineers a solution very similar to this, based on this core technology for the U.S. Office of Naval Research. And I became really personally inspired by what a modular technology that could do that was using water in a low impact way. And so as we were working on this, there was some interest from the Department of Energy. They also began to fund it, at which point, if you know much about defense contracting, when things stop being defense, they stop being interesting. And so it sort of sat on the shelf for about 2 years without any investment, before I finally said, hey, if nothing's going to be done with this, what would it look like if I did? I was watching, the exponential growth of renewables and being really excited about that and wanting to bring something that I felt was sustainable to the table. And so what I did after 2 years is I went back to our old Georgia Tech hydrodynamics professors who had originally designed this, and I said, hey, do you want to go in on this business with me? And they said, sure, but by the way, we're actually not even at Georgia Tech anymore. And so they're still a part of the business, and they are the hydrodynamic brains and fluid mechanics brains behind the vertical axis turbine. And we have been pursuing the vertical axis arrangement since day one, based on their recommendation, and they are our lead hydrodynamicist is now the head of fluid mechanics at the University College London, and is a well-known figure in hydrokinetics, both for tidal as well as for riverine systems. And so this is one that, while you heard me already say, we are not oceanic, we're not offshore. This is already a bidirectional system that would have a natural evolution into that space if and when those types of systems become more feasible. Yes?
Is there a minimum size ditch in terms of CFS that you look at applying this to?
Yeah, so the most important variable for the performance of the system is the 2D inlet velocity to the turbine. And so essentially we look for sites that have a baseline flow velocity of between 1 and 1.5 meters per second, and that's 2D. So then when you look at, volume-wise, for minimum size, you could take just 1/2, and that's 1.6 meters wide, and we have a 80 centimeter tall smallest rotor. So whoever can do the math in here fastest for me, it's going to end up being somewhere around 150 to 200 CFS is going to be sort of your minimum. We prefer to have sites that have more in the 300 to 500 range when you look at having the full double system and achieving those kinds of velocities. But there's other factors at play too. A higher slope canal is going to have higher velocities, shallower flows, and quite frankly, the energy is still there in a different sort of configuration. And so we'll look at everything and tell you. We have actually a very simple site checklist that you can fill out about a site that you may know, and we can tell you very quickly feasibility, power potential, number of units, and things like that. But really sort of a minimum of 150 to 200 CFS.
Can these things like get impeded, like if you're putting them too close together? Can you kind of like cause a backflow kind of situation?
Yeah, absolutely. And that's really the example we give when someone says, well, hey, this looks super simple. What happens if someone copies it and just goes and plunks them in the channel everywhere? And there's a real risk to that. Not understanding how the water flows and how to optimize the hydraulic impact, not only statically but dynamically, is very, very important. We take a lot of care in understanding the integration of this system into channels, and if you put them back to back, you'd certainly choke the flow.
And I see it's distributed,
Mm-hmm.
and I'm thinking through your whole talk, like, this is really kind of transmission related because you've got to have wires, and like you've got to, so, but what was also occurring to me is this possibly a bridge fuel instead of gas? Is that, or am I way off?
No, you're not way off. I mean, I think you have to look at the alternatives that are available to you in the specific situation, and in some cases, yeah, this may displace a gas need that you have. In this particular case, too, Emrgy as a small company, there's also, startup dynamics at play here too. If anyone has started their own business before or has grown a business, you know that you have to find a way into the market that's not going to put you out of business in the process, right? And so as opposed to going and trying to sell, one here that goes to this pump and one here that goes to this house and one here that goes to that, we are today very strict about approaching sites where we can develop many systems in an array and have one client that can manage all of that. And so as a result of that, yes, you need to have the wiring to configure this whole array together. You need to apply it to the grid. But eventually, you can imagine embodiments of this that would be direct connections or off-grid opportunities. It's just, it would be quite a challenge to be able to do that sustainably today. But yes, I think you're right on track. Yes.
I'm not sure I understand roughly what potential do you see within the state of Colorado for this technology? How important, how big a dent could it make?
So that's a great question, and one that we are pursuing the answer to that too every day. I can show you, the specific map that we've created of all of the, areas of excitement and energy in canals around the state of Colorado, and we see a significant potential. I would say at this time, it's more anecdotal than truly quantitative, just because it's taking us quite a while to actually crunch all of that power potential and then compare that to the overall energy mix. But I talk to folks like over at United Power who have said to me, our district isn't great for solar, it isn't great for wind. If we're really going to be serious about renewables, we need to be thinking about something like this. We're looking at projects from Grand Junction all the way. We've got folks in Fort Collins today and tomorrow with irrigators there. And so we have identified and actually have proposals under development on about 1/4 to 1/2 megawatt right now. But obviously we've been at this for months, not even really years yet. And we see the opportunity here to be several dozen times that which we've already even identified.
Could you describe how extensive your operation is with Denver Water?
Mm-hmm.
And is there more exploration of Denver Water infrastructure?
Oh yeah, absolutely. And so this particular channel that you saw in the picture, it's 9 miles long. It goes from Gross Dam to Ralston Reservoir. We have 10 modules, 100 kilowatts in about 1,000 feet. So the opportunity you imagine for scaling is quite significant. And this particular site, like many in the Denver water system, because what they're doing is bringing water into the city for eventual drinking water treatment, is an operational opportunity as well. You know, today they operate really single-mindedly on water delivery. So they'll, you know, one day they don't send very much water. Another day, maybe it's a lot. And when you think about what the system actually is, it's one reservoir upstream, higher elevation, one reservoir downstream, lower elevation, and they're just maintaining levels. And so when you think about, you know, all the investment into pump storage and things like that, you know, this is a very similar type of operation where if you could really convince them of how they could optimize their power production by running the channel at more strategic times, it could be a really powerful case study and power project. And that's one of, I think, 7 major canals with Denver Water. And then also I was just with their head of hydropower a couple of weeks back where we talked about 4 tail race opportunities as well in 4 of Denver Water's dams. And so there are, the thing that I hope you're seeing here is that there's a lot of opportunity, but unfortunately it's because of the underdevelopment of the industry, it's having to turn over each individual rock everywhere that you go and trying to map all of these out ourselves as opposed to really having a more proactive view on what the market actually is.
One final question.
Yeah.
Do you have any idea about the potential on the other side of the continental divide, that vast collection system in the Fraser Valley?
I wish I had a specific number for you. And when I come, maybe I'll come back to one of these meetings in, you know, a couple of months and try to have a more quantitative figure, because it is something we work on daily. My interns hate me, but it's a very important effort that we're working on to really understand that, because we have a lot of inbound, you know, unsolicited interest of people working in that area and people working all over saying, why is this not more common? So we hope that it will be. Yes.
So I love the concept for all the reasons you mentioned, the modularity, the simplicity, the replicability. I have one nagging concern, and that's based on the fact that in the physical world, you don't usually get something for nothing. So the owners and operators of these water distribution systems, what are they giving up as you extract so much of kinetic energy from their flow? And I can see it like in the foothills of the Rocky Mountains. There's probably plenty of slope there, so it's not an issue. But in the plains and like the Central Valley of California, it's pretty darn flat.
Yeah.
And they have, you know, lifting stations to keep the water moving. So are you robbing Peter to pay Paul as you extract energy from the stream?
It's a great question, and in some areas, yes. Like, for example, I was just with the Central Arizona project a few weeks ago, which you know, when you look at it on its face, it's like the holy grail for something like this. You know, massive canal system serving major parts of Arizona. And, you know, interestingly, 100% of their water is pumped uphill. They use massive amounts of electricity. They don't even, you know, at least in California, they're pumping up to overcome elevation changes that they have to, and then it flows by gravity down to the next pumping station with the next elevation change. And that's really from a necessity to move to one location. But for example, the CAP, they're 100% is uphill from start to finish. And so obviously, you know, we can't work against their pumping activity to generate power. That would be, you know, that wouldn't work with the laws of physics, yeah. And of course, you know, there are other areas, as I mentioned, slope of the, gravity is our friend. I mean, all hydro at the end of the day is working from some element of gravity. We are working on the smallest elements of gravity, not taking into consideration a major elevation drop, but we still have to have gravity. If you don't have any slope at all, then there is no acceleration due to gravity of the water that can be, you know, converted into energy. And so, you know, we prioritize sites that have a slope that, a sufficient slope that results in significant excess energy, but different areas of the country definitely have less potential than others. But then you have to ask the question of, okay, well, maybe what are the specific value propositions in these areas, and is it better for them to have a little bit of energy or none? So I think it'll be situational. But yes, I think you're absolutely right. We have to have the natural energy there.
Estimation of what's the practical limit on, say, the percentage of energy in the flow that you could remove without negatively impacting the hydro?
It really varies. Unfortunately, as much as I want to create a cookie cutter solution that can be applied everywhere, no two water flows are really exactly the same, sadly, for me. But when you look at these sites, some channels, for example, were designed by, like CAP, for example, designed by an excellent engineer who doesn't have 1% of energy, excess energy in that channel. Whereas there are others, there's a site in Idaho we're looking at right now that has something like 80 kilowatts of available energy, per cross section that due to its slope, it recovers after going through our system in like 7 feet or something like that. So it's a highly excess energy site that can be extracted. So it's hard to put a sweeping number on all sites, but this is something that is not too good to be true in the sense that every single channel you look at as you walk down the street isn't the perfect application for this. But there are many applications that, when we take it through our 9 criteria algorithm through our program, seem to be pretty attractive for power purposes.
What happens when you have a flood? Do you have to curtail? Do you get too much generation? And also, have you considered batteries to back up?
So another reason why we focus on infrastructure is that these systems typically have gates and other mechanisms that protect them from flooding events. If there is an overflow of some sort, as I mentioned before, we can dynamically operate them to stall them or keep them from running to make sure that they're not overspinning or something like that. And what was your second question?
If you get too much energy coming out.
Yeah, that's all regulated through the electrical system. No grid would let us connect to them if we were going to just pour excess energy in there. So we have voltage regulation and frequency regulation and anti-islanding issues that keep that from happening.
If you have too much, do you use like micro batteries, like for wind?
You certainly can. We currently, advertise this as a storage-free system since we're using the natural stored energy in the water. But, interestingly, compared to the alternatives, with the more intermittent renewables, you have to oversize the capacity and store that in batteries for when you don't have generation. Whereas for this, if you needed something, if you were doing an off-grid system, you could undersize the system capacity because it's operating all night. You don't need that power and store that power instead. So the economics work out a little bit more attractively. Yes, I don't know where to go. Maybe these 3. Yeah, go ahead.
So in the case of the Denver water system, are they basically putting that energy into the grid?
They are.
Is that with special arrangements of Excel? Or?
Yeah, so that's been,
Because I imagine that's another big issue.
it's been quite complex. It's still not done yet. Basically, to keep a very long story short, this was Excel's service territory, and United Power has been a really great partner and potentially a long-term partner, and they just recently completed a real estate swap to swap service territories so that this is now United Power service territory, and Denver Water will be net metering a United Power bill. But it's, as you might imagine, those types of swaps aren't exactly quick and easy activities. So, but it'll be a net metered. Denver Water, as you may know, they're building the North Water Treatment Plant there at the Ralston Reservoir site. And so it'll be a brand new water treatment plant. While it does have a lot of energy efficiency and generation technology there, it will still have an energy bill, and this will be part of the net metered consumption off that.
Is there any concern about, you said there's not much concern about someone coming in and plopping these down and doing exactly what you do, because you put in things kind of, we understand the flow of water and that's our expertise. What about someone cutting you on cost? Because right now you said that was a bit prohibitive. Have you had any issues giving contracts based on upfront costs? And if someone were to come in and say, you know, just mechanically design this for cheaper, or is there a concern there? Are you working to kind of cut the cost of it?
I would warn my customers to be wary of that because the cost driver in this isn't fancy components or fancy extras. It's the fact that when this runs continuously, it hits 1 million cycles in a month and a half. And so if you're going to just cobble something together and throw it out there, you're going to hit the fatigue limit on something like this really, really fast. And so most of the cost that's associated is in making sure that this is going to live and live for a really long time.
On that point, what's the lifespan of an array, individual maybe the system, and what's the maintenance update with here?
Yeah, so in terms of lifespan, we use, as I mentioned before, similar components, meaning similar bearing styles, similar shafts and rotating components and gearboxes and drives and motors as other hydro. We're not using anything that's not conventionally seen in hydro. And so if properly maintained, these should have an extremely long life similar to other hydro systems. We do have a regular maintenance schedule. I think it's 40,000 hours or something like that for underwater maintenance, given how infrequently sometimes these channels can be shut off. And then we have a more regular routine maintenance for above water maintenance. And that's done either by us or a contractor or by the client. In fact, Denver Water has many technicians who work out at this site. They service these themselves. But the goal is that this is a very robust piece of industrial hardware. So while certainly we may not be the lowest cost leader, one of the drivers for partnering with GE is so we can have the supply chain power, but also be able to still supply super robust equipment. Okay, yes?
How does drought history and current drought factor into business?
It's a great question, and one that we debate quite often, because it's what we are tasked with doing is trying to work with customers to project how this may benefit them in the future. One of the only ways that we can project the future is by looking at the past. Although I wish there was a better way, because as we know, our climate patterns are changing, and what we believe we're going to see are more extremely wet years and more extremely dry years, not so many moderate years based on the trends that we're seeing. But when you look historically at a number of these sites, California had its worst drought in history, 2015, 16, 14, 15, and 16. And so, there are challenges in how we use drought and water discharge histories to project the future. We are refining that every day. In the event of a drought, as I'm sure we all know, in renewables, no resource, no power. So no water, no power. That's unfortunately just the sad reality. But we, of course, that's one of the values also of being an infrastructure is the conveyance patterns and contracts that are really sort of crucial to human health and to industry for water to run. And so even in drought times, the major arteries of water, typically are still feeding feeding the channels, or else we would be in a health crisis.
So given the maintenance schedules that you just talked about, it sounds like these turbines are a lot less susceptible to the silt that might be carried and wear that would occur to other types of turbines compared to these. Is that true?
We do have silt mechanisms built into the system because we do anticipate it. And clearly I want to be transparent that we don't have 10 years of operating history on these yet to really be able to tell. They may need further maintenance. We may end up seeing more abrasion than we're expecting. There's still a lot to learn about this, and another area for good, bright interns and other engineers who are interested. We have a site very close to here that we'd love to take more data on. And so, yeah, I think that that's still to be seen. There are some differences around sort of rotational speeds and configurations between bearings and rotor blades and things like that are some, you could make an argument that it is slightly different than other types of turbines when it reacts to that, but not necessarily we didn't proactively plan for that. We just put conventional silt, extraction mechanisms into the floor. Mm-hmm.
First off, thanks for a presentation on emergent renewable technology. That's the first I really got an in-depth look at what you're doing. Not really a two-part question, because two different ones. The first one is water rights and water law and that sort of thing an impediment or like keeping up with this train of thought and accepting this sort of thing? And then someone previously was kind of asking along the lines of, the flux reduction of, a train of these units. Have you considered that as a possible flood mitigation benefit, or something in the sense that actually slowing down water could have a net benefit in some place like California, where the dam structures there are not necessarily dispatched based on power generation, but are part of flood control?
Yeah, great questions. I'll start with the second one first. We have not completed an in-depth study around water speed reduction, and especially because depending on the slope, but the energy unfortunately recovers in a relatively short distance. We haven't done an in-depth study of how that could be helpful. Potentially, if you did use many of these systems, you could see that. Yeah, exactly. Although, unfortunately, in addition to that, you would see a propagation of upstream rise too, so you'd have to sort of take both into consideration. But we have had serious inquiries out of particularly flood-prone Latin American countries, where they're looking for solutions that can accomplish both a desperate need for clean energy as well as flood mitigation strategies. And we've looked at applications of putting these under our street flood grates, where all the floodwaters are rushing underground, to be able to help slow some of that down and take energy out. And it's definitely a fascinating topic that we'd like to look further into, but haven't been able to really fully explore yet. And then related to water law and water rights, when I started this business, I went and saw a colleague of mine who works in the solar industry, and his quote to me was, are you crazy? What we're doing is hard enough in developing these renewables, and you're going to go into an area where wars are fought over water? This is insane. And so, I was sort of prepared for the worst. And, we still have yet to see it become a huge detriment or impediment to what we're doing. There are definitely many complexities that must be understood around how essentially, how all kinds of water rights, water wheeling, water sales. You know, this district works with that district and they have a handshake deal, so their water flows aren't even shown in the contracts. And, you know, there's a lot of things going on that we have to find expertise in to be able to really fully understand what our market potential is. But it really, you know, we see it as an opportunity because this is it's essentially a feedstock for our system that is a commodity that could be harnessed for good. And so it's definitely far more complicated than, you know, understanding, you know, just when it might be raining or something like that. But we have yet to see it become, you know, a sweeping impediment. For example, you know, FERC, in terms of developing these systems and selling the power, has already approved, far before our time, a qualifying conduit hydropower exemption, to where hydropower built in water conduits for moving water from one point to another are exempt from having to go through FERC licensing up to a certain capacity. And so, you know, that's a huge facilitator for us that, had that not been previously lobbied for and achieved, we might see that as a big issue. And that's one of the reasons why we don't go into rivers, is that exemption doesn't exist there. But it's a great question. Any other questions? Yes.
So did I see in one of the first films I saw, is that they were counter-rotating?
Yes. Yep, you'll see here they counter-rotate, taking into consideration the highest flow velocities on the outside of the turbine as a result of that acceleration of flow through the concrete.
They keep it from creeping. But then we use only one motor.
Yeah, this was sort of a brainchild of mine. That is a whole chapter in the book of why I wanted to do it that way. Part of Emrgy's intellectual property portfolio is also a next generation gearing and drive system that I wanted to put on these as well, but I knew they were too expensive to do two. So I mechanically coupled them to be able to put one for both turbines, but this actually is not how we build them now. We use all the same stuff. We use dual drive just to eliminate the mechanical coupling. Yeah, and you can see that in the renderings. Well, I really loved being here with all of you. I hope I was able to give you some insight into distributed hydroelectric and our approach to it. I have my business card and my contact information was on the last slide, and I would love to hear any further ideas or references or people that we should talk to that you would recommend. And I look forward to talking with you all either after this or hopefully in the future as we're building more of these systems.